Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through what was learned in week 9. So we just went through total change and kinematics, although kinematics is an example of total change. So the idea of total change is if you have the rate of change of a function, you just integrate that to get the actual function. So let's look at this example. Rate of change of the volume of water in a creek is given by this function, T minutes, V in litres, and we're going to find how many litres flow into the creek or the change in volume of the creek in the first 30 minutes. So this is a creek where water is flowing in and out, and we're going to find the difference in volume after 30 minutes compared with after 0 minutes. So because we have the rate of change function here, all we need to do is integrate it. So we're going to integrate between 0 and 30 because first 30 minutes means from time 0 to time 30 minutes, and t is in minutes. So we're going to integrate this function here. So you know how to integrate functions like this. We've done it 1,000 times. Because it's a polynomial in t, we're simply going to increase the power of t by 1 and divide by the new power. Increase the power of t by 1, divide by the new power, and we'll evaluate this between 0 and 30. So if I substitute 30 into this formula here, t equals 30, I get 900. If I substitute 0 into this formula, I get 0. So the total change in volume is 900 litres. So water's flowing in and out of the creek, and in the first 30 minutes, after 30 minutes, there's 900 litres more than when we began. So I want to make a point here. We can't, from this information, figure out how many litres are actually in the creek. We can't even figure out how many litres were in the creek to begin with. The reason is if we integrate this to find the volume function, we don't have enough information to find the constant of integration. So there could have been 1,000,000 litres to begin with, or there could have been 1 litre to begin with. We don't really know. All we know is the change in volume. We don't know how many litres there are after 30 minutes. We don't know how many litres there were originally, but we know that there are 900 more litres after 30 minutes than there were at the start. And that's what we're finding with total change. So we've integrated the rate of change of volume function to find the total change in volume. So if you want to find the total change in something, and you know the rate of change function, you can just integrate the rate of change function. That will tell you the total change in the function. Now let's look at a kinematics question. So let's look at this question here. Car traveling 54 kilometers an hour, driver slams on the brakes at a rate of 10 meters per second squared, and how far will he travel after braking before he stops? So what we're looking for here is the change in displacement, and usually we use xt for displacement. That's what we're after. So using what we learned about total change, that's just going to be the integral of velocity between two limits here. So in order to solve this problem, I need to find the velocity function. Now I'm told that the acceleration is minus 10 meters per second squared. The acceleration is negative as the car is slowing down. It's decelerating at 10 meters per second squared, so it's accelerating at minus 10 meters per second squared. So because acceleration is the rate of change of velocity, to find velocity, we're just going to integrate acceleration, and it's with respect to t time. So the velocity is going to be minus 10t plus some constant. So we don't have any limits here. Why is that? Well, we need to find the velocity function. We don't want a numerical answer here. We don't want to find the change in velocity. We need the velocity function. So we need to figure out what this c is. This is an indefinite integral, which is why there is a c value. So this c value is just going to be the initial velocity. But because the acceleration is meters per second squared, I need to get this in meters per second. Now, to go from kilometers per hour to meters per second, you actually just need to divide by 3.6. So if if I divide that, I get 15 meters per second. That is the initial velocity. So what that means is that this value c is 15. The velocity function is actually minus 10t plus 15. This number being the initial velocity in meters per second. So now that I've got the velocity function, I can just integrate it to find the change in displacement. So what are these two values here? Well, I can just have time 0 being when I started braking, but when did I stop braking? When did the car stop braking? Well, that would be when the velocity is equal to 0. So if the velocity is equal to 0, we get minus 10t plus 15 equals 0. Easy to solve. Subtract 15 from both sides. Divide by minus 10, you get t equals 1.5. So this car traveled for 1.5 seconds. He put on the brakes and 1.5 seconds later the car stopped. So I'm finding the change in displacement between 0 and 1.5 seconds. So the change in displacement is just going to be the integral from 0 to 1.5 of my velocity function, which was minus 10t plus 15. So once again, we know how to integrate this. We're just going to increase the power by 1 and divide by the new power. So I get minus 5t squared plus 15t between 0 and 1.5. So substituting 1.5 for t into this formula, I get 11.25. And of course, if I were to substitute t equals 0 into the formula, I would get 0. So it's just 11.25 minus 0, 11.25 meters, because everything else was in meters. So that means the car, after the driver hit the brakes, it will travel 11.25 meters in this 1.5 seconds. So this is just an example of total change. The total change in displacement is just the integral of velocity, because velocity is the rate of change of displacement. All right, thank you so much for tuning into this video. Keep your head up. You're a superstar. You're doing well. This is the luckiest maths teacher in the world. Have a great day.